Hey everyone. Today we're going to be talking about waves again and light and sound waves and things like this. I want you to know that I made this video in parts and I started it in the science office and it was nice and funny and whatever. And then I made the whole entire video. And then when I finished, the first chunk of my video was corrupt or whatever, so it wouldn't work. So it's going to be a little confusing at the beginning here because I'm talking about being in different places, but just know that I was in the science office and introed it all. But now I'm just going to intro it here in my house. So technology doesn't always go well. It's totally fine. I understand it because it happens to me too. So, with that being said, let's get into it. Psych! Now I'm at home. So I started recording the video at school. Then I realized that we had already done a lot of this stuff because you guys actually went faster than I was expecting. So today is kind of a review. I'm going to show you the Slinky demo again, just as a reminder. Then I'm going to show you about the Doppler effect, which is something that you've heard before. You just didn't know what it was or why it was happening. And just kind of reviewing some of this light stuff. And then tomorrow, we're going to start a new topic about something called the HR diagram. So for today, you're just going to be listening to these notes, and then there'll be some questions that I'd like you to answer at the end so that I can see if you're understanding what we're talking about. I've had experience with waves in the past, both with water waves, right? In the ocean, hopefully we've all heard that there are waves in the ocean. There are also sound waves that you may not know you've heard, but you are hearing all the time, and you can actually hear a really cool phenomena that we're going to talk about in a little bit here. And then the light waves, and that's where it gets a little confusing. But when we're talking about waves, you can keep thinking back to the things that make sense to you, like ocean waves. If we're talking about ocean waves, and we have our picture here, you can think that this is just like an ocean wave. And there's the top of an ocean wave and the top of the next one behind it, and that's the wavelength. We probably wouldn't see an ocean wave like this. That would be kind of scary with such a short wavelength. But each wave does have a different wavelength. Some are longer, some are shorter. And that changes the frequency, and that also changes the energy. So when you're thinking about waves, try to think back to the ocean and where you've actually seen a wave happening, or maybe just seen a video, but whatever, it works just the same. So one way that we're going to talk about waves today is by looking at a slinky. So this, where is it? This right here is the world's worst slinky in the world. Look at this thing. It doesn't go together. It's completely broken. If anyone knows how to fix a slinky, please send help. But I'm going to try to just use this part of the slinky that's not quite so broken. And I hope that you can see it. So this is kind of like the wave that you just drew. You can see that it goes up and down. You can see the wavelength is from the top of one to the top of the next one. That's the wavelength, right? And there's some sort of frequency going on here. If I want to change the wavelength and I want to make the wavelength longer, what do I need to do to my slinky? I need to stretch my slinky. Do you see how the wavelength is getting longer? It used to be here, and the wavelength was from the top to the top. And then when I stretch the slinky, the wave gets longer. The wavelength gets longer. I could also make my slinky have a shorter wavelength. How could I do that? Yeah, I just squish my slinky, and you can see that the waves are getting much smaller. And the frequency is getting a lot higher. There's more waves happening in a small, the same amount of waves are happening, but it's in a smaller space versus here. Okay, so I can actually stretch or squish my wave, and that will change the wavelength, and it will change the frequency of my wave. Okay. All right, so we can talk about wavelength, top to top. We can talk about frequency, how many times something happens. And if I change the wavelength, I'm also going to change the energy in the wave. Okay, because remember, I can talk about those three things: wavelength, frequency, and energy. So here's my wave. And I am going to stretch my wave, giving it a lower wavelength. What is going to happen to the energy in the wave? There's less energy, because when you stretch a wave, longer waves have less energy, right? They look like they have less energy. I could also take my slinky and I could squish it. I'm getting a shorter wavelength, a higher frequency. What's going to happen to the energy in my wave? It's going to have more energy. Okay. So we can do things to waves to change how much energy that they have. So you might not realize it, but you have experienced changing waves before in your life. And I know that you have. If you have ever heard a car go past you, or an ambulance, or fire truck, or something go by you, the best answer is the best example is just like a car going by you really fast. You can actually hear the waves changing. So if you were in class right now, I'd ask you to do a little voice demo of what it sounds like when a car goes by. It sounds something like this. Meow. Did you hear the pitch change? Did you hear the sound actually change? Meow. It's like up here and then it drops off. The sound is not going where the pitch would go up. That's not what happens. And it doesn't stay the same the whole time. I almost did it automatically. It doesn't sound like that. When a car goes flying by you, you hear it go meow. Especially like at a race car. I'm just having the that remembrance of like watching NASCAR and hearing the cars go by you. So when you hear that, you are actually hearing the sound waves changing. That change in pitch is called the Doppler effect. I'm going to spell it. Doppler effect. Okay. The Doppler effect is what happens when waves get either squished or pulled apart. And we can hear the Doppler effect when we hear a car whizzing past us, especially if it's like blowing on its horn. So I just tried to make a video where I recorded a YouTube video with the horn blasting. It didn't work. So in order to get the full effect, I'd like you to go to YouTube right now. And I'd like you to look up Doppler effect and look up like horn blaring or something. Doppler effect, horn blaring. Look this up on YouTube so that you can hear it and you can hear that pitch change. And while you're watching the video, I want you to think about, why would that be happening? Why would the car's pitch be changing, knowing that it has something to do with the sound waves getting squished or pulled apart? So go watch that video. Okay, so hopefully you watched that video and you got to hear the Doppler effect. So there's Doppler effect again. And remember that it's just sound waves being either squished or stretched. So now I'm going to describe the science of why that is happening. What is happening to those sound waves that make the car sound different when it's moving. Okay, so basically, if a car was not moving at all, it would give off sound waves when it beeped its horn that looked something like this. And I know that you all love my drawings. So if the horn is beeping, the sound waves are coming off of the horn equally in all directions. This kind of looks like the waves, like if you dropped a rock into a body of water, into a lake or something, you would see all these waves come out from it. It's the same thing with the horn. So these are the sound waves that are coming from the beep. And if I was a person standing here in front of the car, I would hear that sound wave and I would say, "Oh God, I need to look out." And if I was standing behind the car, I would hear the same thing. Okay, so I would still hear the car, I would hear the sound waves, and the sound waves would look something like this, where it's equal waves in all directions. That's if the car is staying in the same place. If the car is moving, it actually changes these sound waves. So I'm going to show you what that would look like. Okay, so now I'm going to get rid of this staying still because the car is not staying still. So the sound waves are going to look different. So here's my car. Beautiful. Here's my person that's standing over here. And the car is moving towards the person. Maybe there's a person over here too. Okay. When the car is moving, instead of having the nice, perfect circle sound waves, the car is actually going to be moving into its sound waves. It's going to be kind of pushing the sound waves towards each other and squishing them together. So instead of being nice and equal, when the car is moving, it's actually going to squish these sound waves really close together on top. Okay, so we went from waves that were like this far apart when it was still, and when the car moves, it squishes all them together so it looks more like this, where they're all really squished together. Okay. And what happens behind the car is it's moving away. And so it actually, the sound waves kind of look like this, where they're getting squished in the front, but stretched really far in the back. So if we're looking at these waves, where is the wavelength bigger and smaller? So the wavelength here is only this big. But the wavelength back here is much, much larger. So because this car is moving, it's squishing the waves. It's making the wavelength much, much shorter in the front. Because remember, the car is moving this way. So it's making these waves much shorter, and it's making these waves much longer in the back. And when you change the size of the wave, you change the sound. So what this person hears is a high pitch. It's going to push those waves. Once it passes this person, it's going to be like this guy over here. It's going to be a lot more stretched out. And when the waves are stretched out, you hear a low pitch. So, and it changes to a low pitch. So the Doppler effect is sound waves getting squished or stretched. And that's happening because the car is moving. The car is moving, and it squishes the waves in front of it and makes them really small. But behind it, it stretches the waves out. So when you stretch or squish a sound wave, you hear a different sound. I'm going to write that down. I'm going to erase some of this because it's getting kind of messy. So if you stretch or squish a sound wave, you get a different pitch. Example, car horn. And remember, the car actually has to be moving. If the car is in the same place and not moving, it just gives off the perfect sound waves. They're not squished or stretched. But when you squish them because the car is moving and stretch them because the car is moving, you get a different pitch or a different sound. Okay, so now we know that we have heard how sound can change based on what you are doing to the wave. Now let's bring that to light. So when you see colors, what you are actually seeing are different wavelengths. So this might be one color, this might be a different color, this might be a different color. When you see the wavelength for red, your eye says, oh, that's red. When you see a different wavelength for green, your eye is able to see the green. So if I have my slinky here and I have my wave, and I take it, and let's say that this is green. Okay. What I'm going to do is I'm going to take my green wave and I'm going to stretch it. That means it's not green anymore because I'm stretching it. I'm changing the wavelength. I'm turning it into a different color. I stretched it. What color have I created now? How about if I take my green, if I put it back? This is really hard to do on video because it's all backwards. If I take my green, and now I'm going to squish it. I'm going to make it have a shorter wavelength. I'm going to have it have more frequency. What color am I going to make? It's really important to look on the electromagnetic spectrum graph, and that will help you remember if you stretch a wave, what color it's going to become, and if you squish a wave, what color it's going to become. So hopefully you are all thinking that if I take this color, green, and I stretch it, it's going to be yellow, orange, red. Look at that beautiful red color. Because I took the wave and I stretched it, I changed the color. I can also do that by squishing it, like we just said. So I can take my green and I can compress it, and I'm turning it into blue, purple, etc., etc. So just like how you can stretch out a wave in sound or squish it, you can do that with light. Except for when you change light waves, what you're actually changing is the color. So now we can relate this to color and to stars. So if we erase all of this, stars are moving as well. And this is something that we're going to talk about a little bit more next week. But I want you to know that stars can also move. So if a star is shining here, it is giving off not sound waves, but it's giving off light waves. So the light would look like this, nice and equal all the way around, if Miss Keenan could draw beautiful circles. And if I was standing here, I would look and I would say, ooh, what a pretty star. So nice. But if the star is moving towards me, it's not going to be these perfect circles, just like the car horn. So I'm going to erase this a little bit, or all the way. If the star is moving towards me, okay, it's going to, remember, it's going to squish the waves in the front and stretch them out in the back. Maybe this one needs to get a little more stretched too. Yeah, this picture is not the best. So these waves up here, they have a shorter wavelength than these waves back here. But remember, stars are giving off light, not sounds. So if we have a star and it's coming towards us, instead of these being sound waves, it's going to be light waves. So what happens when we squish a light wave? When we squish a when we squish a light wave, we make the wavelength smaller. So if we were like this before, now we're squishing it, so we're like this. That color is more like blue. So this star might look a little bit more blue than it's supposed to. How about over here? We're taking the light wave and we are stretching the light wave out. To this person, the star is moving away. The star is moving away from them. So what color would this person see? Stretching the wave out. So instead of looking like this, it's going to look like this. That's more red. So this is just another example of how scientists are able to use light, or astronomers use light to study stars and how they are moving and where they are going and how fast they are moving. Because if they're moving faster, they're going to squish the front even more and drag the back out even more. So they will look even more blue, or maybe towards purpley. We're going to be talking about this and how this is evidence for the Big Bang next week. But for now, I want you to just feel comfortable with the idea of photons and that photons are moving. And remember, on these waves, these are all photons. So these are photons getting squished together, and these are photons being stretched apart. So I want you to be, actually, let me write down some of the stuff you should be comfortable with. So I'm going to write, are you comfortable? Oops, I forgot the L. With photons. And remember, those are coming from the light source, falling down and hitting your eyeball. Are you comfortable with the electromagnetic spectrum? And how light travels in waves? So these photons are traveling in waves. And we can either stretch those waves or we can squish those waves. And if we do that to light waves, let me put it under, wow, that's really dark. Light waves, if we do that to light waves, we make a different color. If we stretch it, it's going to turn more red. If we squish it, it's going to turn more blue. And if we do it to sound waves, it's going to change the sound or the pitch. So it's either going to be a high pitch if they're really close or a low pitch if they're stretched out. So you should feel comfortable with all of these things: photons, electromagnetic spectrum, and how light travels in waves, and that we can take these waves and manipulate them to change colors and to change the pitch. So there's a couple questions I'm going to ask you now that are going to give me an idea if you understand what we're talking about. So please answer those questions to the best of your ability, and then you are done for the day.